assignments, doubts, exams. We have got you back. EduPlanner make every chapter easy to understand. Stay tuned, learn more, grow with us.
For this problem, we're given the situation where there is an object hanging from a string, or a spring, and initially the object is held at rest, where the spring is in its rest position, and the object is just being held there, and that position is designated as yi. And then the object is released and it's allowed to start oscillating up and down. And the lowest point reaches 10 centimeters below yi. And we're being asked to figure out from that what is the frequency of the oscillation. And so when we think about this with the object oscillating, if this is the rest point and the lowest point is 10 centimeters, that means our point of equilibrium is actually going to be right around 5, or right at 5 centimeters, the halfway point between the highest and the lowest point. So we know that our amplitude is going to be 5 centimeters, or we can just go ahead and put that right into meters, so 0.05 meters is going to be our amplitude. At this point, when our object is at equilibrium, that is going to be when the force of the spring pulling the object upward is going to be equal to the force of the weight, or mass and gravity, pulling it downward. So we can write the equation, the spring constant times the displacement, and this situation is equal to the mass times gravity. So we're going to be rearranging this to actually solve for our spring constant, because our spring constant in this case is going to equal mass times gravity divided by the position. And in this case, our position is actually our amplitude. So we're trying to find frequency. Well, how does this get us to frequency? Well, omega, we know that omega equals 2 pi times our frequency. Omega also equals the square root of our spring constant divided by our mass. So we can now actually take this and substitute it in for that term, and take these two equations and make them equal to each other. So in that case, we end up with having the equation 2 pi f equals the square root of mass times gravity divided by displacement divided by mass. So in this case, our masses are going to end up dividing out, so we can actually rewrite this equation as 2 pi f equals the square root of gravity divided by our displacement. And then taking that even further, we get frequency equals the square root of gravity divided by amplitude divided by 2 pi. And when we substitute in our known values, we have the square root of 9.8. Again, we're going from the point of equilibrium, so we're going to use our amplitude, so 0.05, all of that divided by 2 pi, and we get that our frequency equals 2.23 hertz. The second part of this question is asking us to find the velocity of the object when the displacement is 8 centimeters below the initial position, so below yi. So if we let the zero potential energy be at the initial position of the object when the spring is unstretched, and we let the downward direction actually be in the positive y-axis, then our initial and potential kinetic energies are 0, And at position y, the potential and kinetic energies can be determined with the following equations, where potential energy equals 1/2 ky squared minus mass times gravity times y, and kinetic energy is 1/2 mv squared. Now if we take those two and make them equal to 0, 0 equals 1/2 ky squared minus mgy plus 1/2 mv squared, we can actually solve for our velocity. So rearranging our equation to solve for velocity, we would have velocity equals the square root of 2gy minus k over mass times y squared. Now, just as before, we can substitute in for k. We can change k into mass times gravity over our position, which then in turn ends up becoming, because this is divided by m, we actually will end up with the equation velocity equals the square root of 2gy minus g over x times y squared, where x is our amplitude. We can make that our amplitude. All right, so now at this point all we have to do is substitute in our known values. So we have velocity equals the square root of 2 times 9.8 times, we said that we wanted to find the velocity at 8 centimeters, so 0.08 meters, minus 9.8 divided by our 0.05 centimeters, which was our amplitude, times, again, our 0.08 meters squared, and that gives us a final velocity of 0.56 meters per second. All right, so the next part is saying, okay, we have that original object, but we're adding a second mass, and that mass is 300 grams. And when we allow it to oscillate, the frequency of this new mass, so our mass 1 plus our mass 2, is actually 1/2 of the original frequency. In other words, we can put this in terms of omega, where our new omega is actually equal, so our new omega is equal to 1/2 of our original omega. And as we did before, we had omega equals the square root of k over m. So k being our spring constant divided by our mass. Now, since it's 1/2, so we can create the equation here where we have k divided by our original mass plus our second mass is equal to 1/2 the square root of k in our original mass, or our original frequency. We could simplify this and, square both sides and simplify it, and we would end up with our original mass plus our additional mass is equal to 4 times our original mass. And we know that our M2 is 300 grams. So we have M plus 300 equals 4M. And then solving for M, we would end up having M equals 300 divided by 3. So in other words, our mass is going to be 100, our original mass is 100 grams, or 0.1 kilograms. Okay, and the final part of the question is asking us to find out what the new equilibrium is going to be when both objects are attached to the spring. And we're going to use the equation K times xm equals our masses, mass 1 plus mass 2 times gravity. And we're going to rearrange that to solve for xm. So xm equals our mass plus our second mass times gravity divided by k. Now we also have k equals mass times omega squared, which can also then be turned into mass times 2 pi times the frequency squared. So our new equation is going to be our new amplitude, our new rest position or equilibrium is going to be our first mass plus our second mass times gravity divided by our mass times 2 pi f squared. And now we can start substituting in our values. So we have xm equals our first mass, which we just found out was 0.1 kilograms, plus, make that a plus the additional 300 grams, or 0.3 kilograms, times 9.8, divided by our original mass was 0.100 kilograms, times 2 pi, and our original frequency was 2.23 hertz, and that's going to be squared. Solving for, plugging all of those numbers in, you should get that your xm equals 0.200 meters, or 20 centimeters.